Now that automobiles have become such an indispensable part of everyday life in many countries of the world, it has been necessary to come to grips with the problems of air pollution caused by exhaust gases. Toyota has therefore developed one emission control system after another to cope with this problem. Do you know what exhaust gases are? They are not simply gases discharged after the fuel has burned. Exhaust gases also include harmful elements like carbon monoxide, or CO, caused by incomplete combustion, hydrocarbons, or HC, from unburnt fuel, and oxides of nitrogen, or NOx, due to excessive combustion temperatures. In addition to exhausted gases, there is also evaporated gas from the fuel system. This is raw hydrocarbon gas, which leaks from the fuel tank or carburetor into the atmosphere. There is also blow-by gas that passes between the piston and the cylinder wall and escapes into the atmosphere via the crankcase, and which contains raw hydrocarbon gas. This table shows the percentage of each type of gas which is related to air pollution. Emission control is needed to prevent the production of hydrocarbons in all types of gas. Pollution of the atmosphere by such harmful substances causes many health-related and other problems for people, animals, and plants, especially in urban areas where automobiles are concentrated. Therefore, emission control has been enforced in the United States of America since 1970, as well as in various other countries throughout the world. Testing is performed with a constant volume sampler, or CVS. Exhaust gas is taken from a vehicle run on a chassis dynamo and tested. The standard emission value range differs from country to country, but the running conditions or modes in which the test is performed follow closely either the US or ECE pattern. In the US, vehicles must be run in the so-called LA4 mode. In Europe, the ECE mode is used. It must be repeated 4 times in succession to be valid. The gases emitted during these road tests must satisfy the various relevant control values. To meet such requirements, emission control systems must be designed which are highly efficient and reliable, but which do not sacrifice the power and fuel economy commonly required of automobiles. There are 3 solutions to the emission problem. To solve the blow-by gas problem, a positive crankcase ventilation, or PCV system, is used to return the blow-by gas from the crankcase to the intake manifold for burning. To solve the problem of evaporated gas from the fuel, a fuel evaporative emission control, or EVAP system, is used, in which a charcoal canister absorbs the evaporated fuel and returns it to the engine. To solve the problem of exhaust gas from the engine, a spark control, or SC system, is used to improve the ignition timing and to reduce engine NOx. And a throttle positioner, or TP system, solves the CO and HC problems by preventing incomplete combustion. For other problems connected with the engine, there is an exhaust gas recirculation, or EGR system, which reduces NOx by returning exhaust gases to the engine. And an air suction, or AS system, which uses outside air to help burn the CO and HC in the emission. For after-treatment of the exhaust gases, there is a three-way and oxidation catalytic, or TWCOC system, using a catalytic converter, which is aided by a closed-loop system using an O2 sensor. We have mentioned the more typical measures to control emissions, but depending on the vehicle, there is also a hot air intake, or HAI system, for heating the air when the engine is cold. A hot idle compensation, or HIC system, to control the air-fuel ratio when the ambient temperature is high. An auxiliary acceleration pump, or AAP system, for increasing the amount of fuel injected when accelerating with a cold engine. A choke opener, or CO system, which controls the choke valve opening to prevent the air-fuel mixture from becoming too rich after engine warm-up, and so on. Let's take a look at these various exhaust emission control systems on an actual 4AF engine. This is the engine of a car unequipped with an emission control system. This is the engine of a car equipped with a typical emission control system to meet America's strictest emission control law, that of 1983. Note that even for the same 1983 emission control law, the emission control system required for a car with an electronic fuel injection system, or EFI, is different from that of a car with a carburetor. Now we would like to show you the main emission control systems used on engines to meet the strictest United States 1983 emission control law. First, let's take a look at the positive crankcase ventilation, or PCV system, for handling blow-by gas. Blow-by gas escapes between the piston and cylinder wall and accumulates between the oil pan and the bottom of the engine block. A PCV valve is installed between the crankcase and the intake manifold to return the blow-by gas to the engine for reburning. The vacuum in the intake manifold causes the PCV valve to open and draw in the gas. To prevent the blow-by gas from returning to the crankcase when the engine is stopped, the PCV valve is designed so that the gas cannot enter it from the opposite direction. Take a look now at the Fuel Evaporative Emission Control, or EVAP system. A charcoal canister is used to absorb the gasoline that has evaporated from the fuel tank and float chamber to prevent it from entering the atmosphere. The canister is filled with activated carbon. The emission control computer switches the vacuum switching valve, or VSV, on or off according to the engine RPM, temperature and throttle valve position, thus sending the evaporated gasoline from the charcoal canister to the intake manifold when appropriate. In this way, the emission control computer acts on the system on the basis of the various data it receives. However, the most important area of emission control is technology to increase the purity of the exhaust gases by improving combustion in the engine. This can be done by retarding the ignition timing in order to lower the combustion chamber temperature. This prevents NOx from forming, which would occur if the temperature were allowed to rise unchecked. One method of doing this is to use a spark control or SC system. This system uses a bimetal vacuum switching valve, or BVSV, which advances the ignition timing when engine temperature is low. Let's see how the SC system is checked. First, warm up the engine. Make sure that the ignition timing is at 15 degrees BTDC with the engine idling at about 800 RPM. Next, remove the vacuum hose from the sub-diaphragm of the distributor and plug up the hole. Make sure that the ignition timing is now 10 degrees BTDC with the engine idling. Finally, reconnect the vacuum hose. If no problems are encountered, the system is normal. Please refer to the repair manual for the inspection of each part of this system. Vehicles unequipped with an emission control system have a vacuum transmitting valve, or VTV, in their SC system, which causes the ignition timing to advance slowly. It does this by gradually releasing the vacuum in the M chamber of the vacuum controller, even when the vacuum is high in the advance port. This VTV is allowed to open easily in one direction by a check valve, allowing the pressure on each side of the VTV to equalize quickly. This in turn causes the ignition timing to be quickly retarded. However, in the opposite direction, the pressure must pass through an orifice with a small diameter, causing it to act gradually on the distributor. This in turn prevents the ignition timing from advancing quickly. Another way to increase the purity of the exhaust gases by improving combustion is to use an automatic hot air intake, or HAI system, and a hot idle compensation, or HIC system. The air cleaner is provided with an HAI diaphragm and an intake air temperature compensator, or ITC valve. This is to prevent CO and HC from forming due to incomplete combustion. In the HAI system, an ITC valve senses the temperature of the incoming air and automatically switches over to air warmed by the exhaust gases when it is cold to help vaporization of the gasoline. Also in the HIC system, when the temperature of the air around the engine becomes high, the ITC valve introduces extra air from outside into the intake manifold to increase the air-fuel ratio during idling. This is the throttle positioner, or TP system. To avoid incomplete combustion and prevent the formation of HC and CO, it is necessary to keep the throttle valve slightly open while decelerating. This is done by a VTV and a TP diaphragm, which operate to ensure that the throttle valve closes gradually and that it does not close all the way. We will now inspect the TP system. First, warm up the engine. Now check the engine idling speed. It should be about 800 RPM. Remove the hose of the TVSV-M port and plug up the port. Remove the vacuum hose from the TP diaphragm and plug up the end of the hose. Make sure that the engine speed is 900 RPM. If adjustment is necessary, do it with the TP adjusting screw. After adjusting, reconnect the vacuum hose and check that the idle speed has returned to 800 RPM. Finally, reconnect the hose to the TVSV-M port. This ends the TP system inspection. For the reduction of NOx, the most important mechanism is the Exhaust Gas Recirculation, or EGR system. NOx is formed by the reaction between the nitrogen and oxygen in the air when the engine combustion temperature becomes too high. The exhaust gas recirculation system reduces this temperature by returning the exhaust gas to the combustion chamber to hinder combustion. In this way, the formation of NOx is kept to a minimum. The mechanism which controls the amount of exhaust gas which is mixed with the air-fuel mixture is the EGR vacuum modulator. First, when the engine is cold and no NOx is being formed, the TVSV, which is equipped with a temperature sensor, does not cause exhaust gas to recirculate. Also, during idling, when the upper edge of the throttle is lower than the EGR port, there is no vacuum to open the valve and consequently no recirculation. When the temperature rises and the upper edge of the throttle valve rises to between the EGR port and the EGR port, the valve opens or closes according to whether vacuum or exhaust pressure acts on the EGR vacuum modulator. First, when the load is light, the manifold vacuum is high. At this time, atmospheric air is drawn into the EGR vacuum modulator, so with only a low vacuum acting on the EGR valve, the valve closes and there is no recirculation. However, when the load is heavy, no air is drawn into the vacuum modulator, but a large vacuum opens the EGR valve a certain amount, and this fixed amount is maintained during the recirculation. When the upper edge of the throttle is higher than the EGR port, the vacuum acting on the EGR vacuum modulator increases, opening the EGR valve widely. This also increases the amount of recirculation. However, with the throttle fully open, that is, under a full load, the EGR valve is closed, and since there is no vacuum from the manifold, there is no recirculation. Let us see now how the EGR system is checked out. Remove the EGR vacuum modulator and clean the filter inside. Using a three-way connector, connect a vacuum gauge between the EGR valve and the vacuum pipe. Make sure that the vacuum gauge is pointing to 0 with the engine RPM at 2000 and the temperature below 50 degrees. Warm up the engine, and again with engine RPM at 2000, make sure that the vacuum gauge reading is low. Remove the hose joining the EGR vacuum modulator to the R port and connect the R port directly to the intake manifold with another hose. Make sure that at this time the vacuum becomes high at 2000 RPM. Remove the vacuum gauge and reconnect the hose. Next, with the engine running, connect the EGR valve directly to the vacuum hose and check that this causes the engine to stop. The check is finished. Return the hose to its original place. In countries where emission controls are strictest, the mechanisms we have seen so far may not be adequate, so a three-way oxidation catalytic, or TWC-OC system, is used to clean the exhaust directly. This system is ideal for lowering the amounts of the three harmful substances, CO, HC, and NOx, together at the same time. NOx is composed of O2 and N2. The system uses the O2 to oxidize with CO and HC to form nitrogen dioxide, or CO2, and water, or H2O, respectively. However, to get this response, the air-fuel ratio must be kept within fine limits close to the theoretical ratio. For this reason, the O2 sensor to control the air-fuel ratio is indispensable in a TWC-OC system. This is the closed-loop system. First, let's see how the O2 sensor works. The O2 sensor senses the concentration of oxygen in the exhaust gas and can tell if the mixture is leaner than the theoretical ratio. The O2 sensor is in the exhaust pipe and consists of an element of zirconium oxide, or ZrO2, coated inside and out with a thin layer of platinum and further covered on the outside with a ceramic coating. The inside takes in air with a high concentration of oxygen, while the outside is exposed to the exhaust gas. When a mixture that is richer than the theoretical air-fuel ratio is burned, the difference in the concentration of oxygen between the inside and outside is large, so a transfer of O2 takes place. Therefore, the oxygen in the air loses electrons at the positive electrode of the platinum and becomes negative ions. This allows it to pass through the zirconium element. The ions give up their electrons again at the negative electrode, forming O2, which is then discharged. This creates an EMF, which acts as feedback to the O2 sensor. However, when the air-fuel mixture is lean, there is no voltage because of the small difference in O2 concentration. The O2 sensor senses the concentration of O2 in the exhaust gas and sends this data to the computer. The method of control by the closed-loop system in a carbureted engine is different from that in an EFI engine. In a carbureted engine, when the O2 sensor senses a slightly rich air-fuel mixture, it adjusts the amount of air at the manifold to supply the ideal air-fuel mixture. In the case of an EFI engine, when a rich mixture is sensed, the amount of fuel injected is reduced to dilute the mixture. When a lean mixture is sensed, the injection amount is increased. Let's have a look at the O2 sensor in action. You can see how the voltage changes according to whether the mixture is rich or lean. If everything is functioning properly, feedback will occur 8 times or more every 10 seconds, with the temperature over 50 degrees and engine RPM at 2,000. We have taken a look at the representative types of emission control systems and talked about how to inspect them. Please remember that it is necessary to check and adjust the ignition timing before inspecting each system. There are many other mechanisms in emission control systems in addition to the ones we have seen here. We hope that you will make a point of understanding each of them by studying the repair manual for each relevant engine. There is a tendency for emission control regulations to become more stringent around the globe. However, Toyota's emission control systems, because of their high technical standards, are well able to comply with these regulations. We expect their success to increase even more through your fine servicing.